So, welcome to the third video in this introductory module series. In this module, we're going to talk about how we can lower the environmental impact of cementitious materials by replacing part of the Portland cement clinker with other cementitious materials. So classically, cement has been clinker, which is ground with a small addition of calcium sulfate, normally referred to as gypsum, to produce cement. And this is what we call ordinary Portland cement, OPC, or plain Portland cement. 50 years ago, this made up practically all of the cement produced. But nowadays, the vast majority of cements produced also contain what are known as supplementary cementitious materials, or SCMs. Now, what are these SCMs? Some examples are limestone, which comes from the quarry, fly ash, which comes from burning coal to produce electricity, slag, which comes from blast furnaces where iron ore is reduced to iron, and natural pozzolans, which are found in nature, and finally calcined clays. Now, these are often byproducts or waste from other industry, and their availability will vary considerably from place to place. If we look at the overall level of substitution of SCMs in cements around the world, we can see in this graph here that just 3 materials make up the overwhelming majority of these substitutes, namely limestone, slag, and fly ash. Secondly, we can see that while a few years ago the level of substitution was increasing, for the last 5 or 6 years, it's remained almost static. Now, before we look at the reasons for this, let's look at these different SCMs in a bit more detail. So first we have limestone. This comes from the same quarry where limestone is excavated for producing the clinker. But the important thing here is because it doesn't pass through the kiln, it doesn't lose its CO2. It's typically interground with the cement during milling, and we find that if we had small levels of addition, up to about 5%, it actually enhances the properties. And this is due to the fact that a small amount of the limestone does react with the aluminase veins, and also because the fine limestone particles enhance the nucleation of the CSH and give a denser microstructure. Now, we don't actually need to use high-quality limestone, although this is often required in standards. The second material is blast furnace slag. This schematic here shows that we have iron, which comes from the iron ore, and slag is the material which is used to help the separation of the iron from the impurities in the iron ore. This material is liquid in the blast furnace and then is poured off. And depending on the cooling, we can either have crystalline material, which really can only be used as aggregate, which is air-cooled slag. We can also make expanded slag, which can be used as lightweight aggregate. But what we're really interested in is when we quench this slag, which is what is known as granulation, and by this very fast cooling with water, then we produce amorphous phases, and these amorphous phases can then dissolve in water and react like the cement grains. Now here we see a picture of the slag. We can see these angular grains. They're made up about 90% or more of amorphous material, and then this is ground, and the breakup of this glass gives these sharp, irregular, glassy materials. This has a very high calcium oxide content and produces what is called a latent hydraulic material. Because of the high calcium content, then we can replace very high amounts of clinker in cement. Typical replacement levels are in the range from 30 to 70%. Now, the problem with slag is that the growth in availability of slag has been not as fast as the growth in availability of cement. So at present, the annual production of slag is only around 8% of the production of clinker, And this proportion is unlikely to increase because we're producing more and more iron and steel from recycled materials, and this means there's less slag available from blast furnaces. Next, we move to fly ash. And as I've said, this is the insoluble, incombustible material which is in the coal. What happens is that during the burning of the coal, little droplets of water form. These droplets then are carried in the flue gas and subsequently recovered by electrostatic precipitation to avoid their dispersion into the atmosphere. Now, because they're very small, they cool quite quickly, and this quick cooling again leads to the formation of amorphous or glassy material. So we have much lower proportion of amorphous material. We typically find that the core of these grains is crystalline. Because of this reason and the chemical composition, where it contains less calcium, this is less reactive than slag, and the typical levels of addition we can make are up to around 30%. Now, the other problem with fly ash is that it's a very heterogeneous material. In this micrograph here, we can see the different grey levels indicate the different chemical composition. And on the right here, we've made a chemical mapping of that fly ash, and the different colours indicate different chemical compositions. So what you can really see is that the chemical composition varies considerably from place to place, and this makes it quite tricky to determine how fly ashes react, and means that one fly ash can behave quite differently from another fly ash. So in this series of slides, we can look at the availability of these SCMs compared to Portland cement. So this red bar shows the amount of Portland cement produced in the world today, just over 4 billion tons. And if we look at these common replacement materials, slag and fly ash, we see that the amounts available are much lower than the amount of Portland cement. So slag, we have about 8% compared to Portland cement, and the vast majority of this is already used either blended with cement or added at the concrete stage. When we come to fly ash, overall we have a somewhat higher amount, but because of that variability, the amount that can be used with cement is quite a bit lower. And these two materials together make up only around 15% of the amount of Portland cement produced today. Now, people have looked for other materials that can be blended in. The other material we have is limestone, we've talked about earlier, and there's effectively unlimited amounts of this material available. But the problem is that we can't add very high amounts without diluting the properties of the cement. And generally, if we have additions above about 10% or so, then the strength and other properties of the cement tends to decrease. Now, people have looked at other materials to use as SCMs, which we see now here on the top. We see natural pozzolan. The amounts used today are really quite small. This could perhaps be increased, but nevertheless, geographically, the distribution of natural pozzolan is very uneven. People have considered vegetable ashes, so notably the ash produced by burning rice husks can be an active addition in cementitious materials, but the amounts available are really quite small. And there are a lot of other problems with these vegetable ashes, such that they're only produced seasonally. They tend to be produced in rural areas where the big demand for cement is in urban areas. And currently, many of these agricultural wastes are used as fertilizers. So if they're taken off the land, they may lead to a problem of soil fertility. People have talked about waste glass, but really we see that the amounts of this are very, very small. And of course, it's much, much better to recycle waste glass into new bottles. And finally, of course, silica fume, which is a very high performance additive widely used to produce high performance concrete, but the amount available are really very, very small. So what else can we have? Now, what we really see is that there's only one material that's available in the kind of quantities we really need, and this is calcined clay. And the amounts of calcined clay really are virtually unlimited. So to summarize that, what we see is that there's no magic solution. Blended cements with SCMs will be the best solution for sustainable cements for the foreseeable future. The traditional SCMs we have are only about 15% compared to the amount of cement we produce, and the only material available in viable quantities apart from these is calcined clay. And even more interesting is the use of a combination of calcined clay with limestone, which we'll talk about in another video of this module. So this material with combination of calcined clay and limestone is what we call limestone calcined clay cement, or LC3. So before summarizing this, I just want to say a short word about alkali activated materials, or geopolymers. The low availability of slag is the main reason why alkali activated materials will not contribute significantly to lowering global CO2 emissions. All the formulations of alkali activated which harden at ambient temperature today contain mainly slag. And as we've seen, the availability of slag is really very low. So if slag is diverted from use in cement blends and concrete to be used in alkali activated materials, then we may be able to say that these alkali activated materials have a lower CO2 emissions, but globally the emissions of other concrete will increase. And in fact, what we need to consider is also the CO2 emissions of the alkali activator. And for these two reasons, the CO2 emissions may be increased at a global level. And in fact, there are very few countries which have really abundant supplies of slag, which would favour the use of alkali activated materials. So one exception in this case is Japan. Okay, so let's summarise what we've seen in this lecture. In this lecture, we've seen that supplementary cementitious materials are an effective way to reduce the amount of clinker in cement or in concrete, and hence to reduce CO2 emissions. Over the past few decades, the average level of substitution has increased to around 20%, and this is made up mainly of slag, fly ash and limestone. Further progress in this respect is mainly limited by the availability of these SCMs. And this limited availability is also the main reason that alkali activated materials cannot have really significant impact on lowering overall emissions from cementitious materials. What we have seen is that the only other material available in the kind of quantities we need is clay, which is active when calcined. And this is particularly interesting when used in combination of limestone. So in the next lecture, we're going to look in detail at the use of calcined clays for cement and concrete. So thank you for listening, and hope to see you next time.